Imagine a clear sky over a combat zone. Peaceful for a moment, maybe.
Yeah, quiet.
Then suddenly, it's not empty anymore. You see dozens, then hundreds of these small, buzzing shapes appear, just filling the air.
Little dots at first, then more and more.
Exactly. And they're not just static targets. They're moving, coordinating, acting with some kind of purpose. And here's the thing. They're not piloted by remote control, not like a typical drone with someone miles away using a joystick.
No human in the direct loop for the flight path, yeah.
These machines are making their own decisions, working together to swarm targets on the ground below. That low hum you might hear at first, it turns into this pervasive, almost menacing cloud. And it's all acting with a speed and coordination that, well, no a single human or even a group of humans trying to react in real time could possibly match.
The speed is just incredible, machine speed.
This picture, this isn't some far-fetched scene from a sci-fi movie, something we might have worried about decades ago.
Right, it felt theoretical for a long time.
But it's becoming the stark reality of autonomous weapon systems on today's battlefields. And it forces us to confront a really challenging, really fundamental question. How far can machines truly go in making life and death decisions in conflict?
That's the core of it, isn't it? The kill decision.
And if they're making those decisions, what does that huge shift mean for all of us? What does it mean for the very nature of conflict itself, for the future of warfare, and maybe even for our basic sense of shared humanity and responsibility?
Yeah, it touches on some deep ethical ground there.
Okay, so let's unpack this. You've brought us a stack of source material articles, research papers, analyses covering these systems, everything from the really deep technical details to the policy debates, the ethical stuff, and how they're actually being used.
That's right.
Our mission in this deep dive is basically to pull out the most important nuggets of knowledge and insight from all these sources. We want to give you, the listener, a clear, well-informed picture of where things stand right now with autonomous weapon systems, understanding the tech, the real-world impact, and, well, the urgent questions they raise.
Exactly. The sources you've gathered give a really comprehensive view. They cover what these systems are, how they're different from, traditional weapons, the key technologies making them possible, and crucially, how they're actually performing on the battlefield today.
Okay.
But they also dig into that complex web of legal discussions, ethical considerations, and the geopolitical forces that are just accelerating their development and deployment. It's a space that's evolving incredibly fast. Moving from theory to widespread use and understanding the nuances is absolutely critical.
Absolutely. So let's start with the basics then.
Yeah.
What exactly counts as an autonomous weapon system, or AWS? We sometimes hear the term lethal autonomous weapon systems or LAWs too. Seems like the terminology itself is part of the discussion.
It is, but the sources tend to converge on a core definition. Essentially, it's a system that, once you activate it, can select and engage targets without further intervention from a human operator during that specific engagement itself.
Okay, during the engagement. That's the key phrase.
That's the critical distinction, yeah. It's not just about spotting a target, it's the system making the decision to actually apply force to that target without a human needing to say, yes, fire now, for that specific strike in that moment.
Okay, so that's the line the sources draw. It's not just automation like a simple tripwire or remote control, like a standard drone pilot.
Exactly. A drone piloted by a human from a ground station, not an AWS by this definition, because the human is constantly in the loop, controlling actions, approving every strike.
Right.
An automated sentry gun that just blasts anything crossing a beam might be automated, but maybe not fully autonomous in the sense of selecting a target based on complex criteria or context. It really is about the machine's ability to make that specific kill decision.
Got it. The decision to use lethal force.
Precisely. And it's really crucial to understand that autonomous isn't a simple on-off switch. It's not like a light switch.
It's a spectrum.
Exactly. The sources really emphasize that autonomy exists along a spectrum, a gradient. It's often described by how much human control is still involved in the decision-making process, especially around using lethal force. People often talk about different loops of human control.
Okay, and the sources break this down into 3 main levels.
Yeah.
Which helps clarify things a lot. Can you walk us through those loops?
Absolutely. The first level, the one closest to traditional remote-controlled systems, is human in the loop, HITL.
HITL. Okay.
In this setup, the autonomous system might do things like search an area, maybe identify potential targets, track them, highlight them for an operator. But, and this is the key part, a human being has to explicitly look at that target information and authorize each and every single engagement.
Every single one.
Every single one. The machine finds something interesting, points it out, but the human verifies it and effectively pulls the trigger or clicks the button for every use of force. It's like the machine is a really sophisticated scout or spotter, but the human is the final decision maker and executor for each individual shot.
Okay, clear. The human is absolutely essential for every strike command. So what's the next step down that gradient? Where does the machine get a bit more independence?
That brings us to human-on-the-loop, HOTL.
On the loop.
Right.
Here, the system is actually capable of operating autonomously, but it's under human supervision. So it can make its own decisions about selecting and engaging targets based on its programming, its rules of engagement, the sensor data it's getting.
But there's a supervisor.
Exactly. There's a human operator who is actively monitoring what the system is doing. This human has the ability to override the system, maybe divert it, or abort the entire mission if something looks wrong, if the system seems to be making a mistake, or maybe if the tactical situation changes suddenly in a way the machine isn't programmed to handle.
So the system acts, makes its own strike decisions within its parameters, but the human is there watching, like a supervisor, ready to intervene and stop it if necessary. It's less about approving every single shot like an HITL, and more about monitoring the system's overall behavior and having that veto power.
Kind of like a safety driver in an autonomous car test, maybe? The car's driving itself, but the human is watching, hands near the wheel, ready to grab control instantly.
That's a pretty good analogy, yeah. Ready to intervene.
And then the third level, the one that, well, seems to generate the most debate and concern.
That would be human-out-of-the-loop. Out of the loop?
This is where the system makes decisions to select and engage targets entirely on its own, without any further human intervention needed during that engagement phase. Once it's activated and sent on its mission, the system identifies targets according to its programming and attacks them autonomously.
So the human launches it, maybe sets some parameters, but then it's on its own for the actual finding and firing. Pretty much. The sources note this is typically reserved for extremely high-speed tasks where human reaction time is just physically too slow to be effective. Think about missile defense.
Right, intercepting something coming in super fast.
Exactly. An incoming missile might be traveling so fast that a human literally wouldn't have the seconds, maybe not even fractions of a second, needed to react, verify, and approve an intercept. In those cases, once the system is authorized to defend a certain area or asset, it handles all the subsequent steps: detection, tracking, targeting, firing completely independently.
That spectrum in, on, out of the loop is really key. It shows we're not talking about one single scary robot killer thing, but a whole range of capabilities with different degrees of human involvement.
Absolutely fundamental to understand that range.
Can you give us some concrete examples from the sources, things that illustrate these different levels or types of systems in the real world?
Sure. The sources provide examples for both defensive and offensive systems. For defensive systems, which are designed to protect assets by reacting to threats coming in, you often see higher levels of autonomy. The thinking is the risk to civilians is generally lower because the system is reacting to an active attack, focusing on specific incoming objects like missiles or drones.
Okay, reacting to an immediate threat. Makes sense.
A prime example mentioned is the U.S. Navy's Phalanx CIWS. That's the close-in weapon system. You've probably seen it. It's that rapid-fire 20-millimeter Gatling gun mounted on warship.
A white dome thing that spins and fires incredibly fast.
That's the one. R2-D2 on steroids, some call it. Its job is to shoot down incoming missiles and drones at very close range very quickly. The sources note that Phalanx can operate autonomously, especially when it switches to a fully automatic mode to handle multiple fast-approaching threats at the same time. It's been used successfully against real missile and drone threats. For its specific task, that split-second interception, it fits squarely into the HOTL concept. Once it's turned on to defend a sector, it makes those microsecond decisions to identify and engage threats all by itself.
Wow. Okay, so HOTL in defensive use is already quite established.
In certain contexts, yes. Another defensive example the sources bring up is Vehicle-Mounted Active Protection Systems, APS. Think of systems like Israel's Iron Fist.
Right, the things you see on tanks now sometimes.
Exactly. These systems use radar and infrared sensors mounted on the tank or armored vehicle to detect incoming threats, things like RPGs or anti-tank guided missiles. When it detects a threat coming in, the Iron Fist autonomously launches a counter-projectile, like a small blast or pellets, to physically intercept and neutralize that incoming round before it hits the vehicle.
So it shoots the missile before the missile hits the tank.
Precisely. And the whole process, from detection to firing the countermeasure, happens in fractions of a second, way faster than a human could react. Depending on its specific configuration and programming, this system autonomously detects and engages threats to protect the vehicle, fitting into that HOTL or potentially even HOTL category for its very specific defensive job.
Those examples really show machines making autonomous defensive decisions at incredible speed. What about offensive systems, the ones designed to go out and attack enemy targets?
An earlier, but still very relevant example mentioned in the sources is the Harpy loitering munition. Israel introduced this back in the 1990s.
Loitering munition meaning it hangs around waiting for a target.
Exactly. The Harpy was designed to be launched and then fly to a designated geographical area and just loiter, circle around. Once it was in that area, its job was to independently search for and then attack radar emitters specifically, things like enemy air defense radars.
So it had hunted radars on its own.
The original concept, yes, it was designed for autonomous engagement of a specific type of target, radar signals, once found within a defined zone without a human needing to be involved in that final decision to dive onto that specific radar detected. Now, its successor, the Harop, often operates in modes closer to human-in-the-loop or human-on-the-loop, where an operator can lock onto a visual target. But the original Harpy really demonstrated that early concept of offensive autonomous target engagement. These types of systems are often called kamikaze drones or suicide drones because, well, they destroy themselves by crashing into their target.
Okay, so we have defensive systems acting autonomously at high speed and offensive systems that can loiter and hunt specific types of targets on their own. None of this happens in a vacuum, though. What are the underlying technologies making this possible? The sources dive into these, right?
Absolutely. Several key technologies are converging right now to make AWS not just feasible, but increasingly effective and, frankly, widespread. First and foremost, you have computer vision and deep learning.
The AI eyes.
Essentially, yes. This is how autonomous systems see and understand their environment and critically how they identify potential targets. Technologies like ULF9, that stands for You Only Look Once, are advanced algorithms. They can rapidly scan an image or a video feed and detect, classify, and draw bounding boxes around objects it recognizes.
Like putting a square around a tank in the video feed.
Exactly. It can identify a tank or a specific type of vehicle or sometimes even people, all in real time, even if they're moving. This real-time object detection is absolutely fundamental. That information, hey, there's a T-72 tank at these coordinates, feeds directly into the weapons missile guidance loop, telling the system where the target is, how to track it, how to adjust its own flight path to hit it. It's like giving the machine eyes that can instantly recognize specific things it's been trained to look for.
And it's not just YOLO, right? There are other approaches.
Correct. The sources also mention things like vision transformers, VIT. These represent a different, sometimes more powerful way of processing visual information. They often allow the system to understand the broader context and the relationships between different objects in a scene, not just identifying individual items in isolation, maybe understanding that a truck is next to a building, for instance.
So they can spot a target and maybe get a better sense of its surroundings.
Yeah.
But where does all this complex processing happen? Does it need big computers back at base?
That's where edge AI chips are crucial. These are specialized processors designed to be very low power, but very efficient at running these complex AI algorithms.
Edge meaning on the device itself.
Exactly, on the edge of the network, right on the drone or the weapon system. Think of chips like the NVIDIA Jetson series or Google's Edge TPUs. They get embedded directly onto the platform. This allows all that heavy AI calculation, the vision processing, the target recognition, the decision-making to happen onboard the machine in real time.
So it doesn't need to constantly send data back and forth.
Right, which is vital if communication links might be jammed, unreliable, or if you just need instant reaction. It's literally putting the AI brain right onto the machine itself. Critical for true autonomy.
That onboard processing seems key.
Okay.
What about navigation? Knowing where they are, especially if GPS is jammed, which happens a lot in conflict zones.
That's handled by techniques like SLAM navigation. SLAM stands for simultaneous localization and mapping.
Okay, localization mapping.
Yeah. It's a clever technique that allows an autonomous system to figure out its own precise position within an environment, while at the same time building a map of that environment as it goes. This is incredibly useful in places where GPS signals are jammed or simply unavailable, what the military calls a GNSS-denied environment.
How does it do that?
It uses data from its various onboard sensors cameras, maybe radar, LiDAR, which uses lasers, inertial measurement units that track movement to build up that understanding of the space around it and its own position within that space. It's like the system is building a dynamic, real-time mental map as it moves through a new place and using that map to know where it is and where it needs to go without relying on external signals like GPS.
Okay, so it can see using AI, process onboard using edge chips, navigate without GPS using SLAM. What about when you have lots of these things working together? You mentioned swarms earlier.
Right, swarming capabilities. This is a huge area of development. It involves networks of multiple autonomous drones or other systems working together, coordinating their actions to achieve a common goal. Instead of each drone being flown individually, they operate as a group.
How do they coordinate? Is there one leader drone?
Sometimes, but often they use decentralized algorithms. Each drone might follow simple rules related to its neighbors, like stay close, avoid collisions, move towards the general objective. It's sometimes called leaderless flocking, inspired by how birds fly in formation or fish school. The complex, coordinated group behavior emerges from these simple, local interactions.
Fascinating. Like emergent behavior.
Exactly. Though you can also have hierarchical command structures, where one drone or a ground station acts as a leader and assigns tasks to the others. But the key is coordination without constant human micromanagement of each unit.
And for those swarms to work, especially under attack, they need to talk to each other reliably, right?
Absolutely critical. If the enemy is trying to jam their communications, the swarm falls apart. So you need robust communication technologies. The sources mention mesh networking and anti-jam optical links.
Mesh networking, like they relay signals through each other.
Precisely. It creates a decentralized web. If one drone gets taken out or jammed, the others can potentially route messages around it. It makes the network much more resilient.
And optical links using lasers.
Yeah, anti-jam optical links, like laser communication. Light is much harder to jam or intercept over certain distances compared to radio waves. So it provides a more secure, stealthy way for units within a swarm or between a swarm and a controller to communicate, even if there's heavy electronic jamming going on. It's all about keeping the team talking and coordinated no matter what.
All this advanced tech, AI, vision, edge chips, SLAM, swarming algorithms, laser comms, sounds like it should belong on massive, expensive platforms. But we're seeing these capabilities pop up in smaller, sometimes really cheap, disposable systems. How do they manage that?
That brings us to a really critical set of design constraints, often summarized by the acronym SWaP-C.
SWaP-C, okay, what's that stand for?
Size, weight, power, and cost. These are the absolute fundamental limits when you're designing these small autonomous systems. Every single gram of weight matters for flight time and maneuverability. Every watt of power consumed affects battery life and mission duration. And every dollar of cost impacts how many you can build and whether you can afford to lose them.
So it's a constant trade-off.
Always. A designer might have to choose a smaller, lighter battery, which means maybe they can't use the most powerful processor, or the drone can't fly as long. Or they might choose a slightly less accurate but much more power-efficient edge AI chip to really stretch out that loitering time. Or maybe a smaller warhead to allow for more fuel or a better sensor. It's this constant balancing act to cram all this sophisticated capability, the sensors, the processor, the communications, the navigation, the weapon itself, into a tiny package that's light enough, power efficient enough, and crucially, affordable enough to be produced in large numbers and potentially treated as expendable, making these smart weapons fit into small, cheap boxes.
So wrapping up this first part then, when we talk about autonomous weapons, it's definitely not a simple on-off switch. It's not one single thing. The source material makes it clear it's a complex gradient of autonomy powered by a whole bunch of rapidly converging technologies, leading to different systems designed for specific jobs with different levels of human control, or sometimes none at all in the final moment.
Precisely. And the really sobering thing is these technologies and the systems they enable, they're not just concepts being debated in labs or shown off at arms fairs anymore. They are having a very real, very significant impact on the ground right now.
Okay, let's shift gears then and really unpack that. Where have we actually seen these systems deployed? Where have they had a noticeable effect in real-world conflicts recently?
The source material seems to point to several conflicts since about 2020 as being a very stark reality check. These ideas moving from the drawing board straight onto the battlefield.
That's absolutely correct. We can trace a pretty clear arc of their increasing use and impact. An early significant indicator was the Nagorno-Karabakh conflict in 2020.
Right, between Azerbaijan and Armenia.
Yes, Azerbaijan made very significant and highly effective use of semi-autonomous loitering munitions and UAVs in that conflict. Notably, systems like the Israeli Harop, which we mentioned, the successor to the Harp.
And what impact did they have there? They were employed very effectively against Armenian air defenses and armored vehicles. The sources highlight how the ability of these drones to be sent to a general area and then autonomously search for and engage specific target types, like those critical radar emitters for air defense systems, played a really key role in suppressing Armenia's defenses and ultimately shaping the tactical outcomes. It was an early, very visible demonstration of how these offensive autonomous capabilities could provide a decisive edge in a contested environment.
So Nagorno-Karabakh was a clear sign of the tactical advantage these systems could offer. But the sources point to a much larger, more recent conflict as really underscoring the impact and, maybe more importantly, the scale these systems can reach, right?
Absolutely. The conflict in Ukraine from 2022 onwards, right through 2025, as covered in the sources, is highlighted as arguably the largest, most intensive deployment of autonomous and semi-autonomous systems we've ever seen. It's become a brutal testing ground and accelerator for development and adoption on all sides.
And the sheer scale and just the variety of systems being used there sounds staggering compared to anything before.
It really is. We've seen, according to the sources, thousands upon thousands of sorties flown by an incredibly diverse range of drones and autonomous systems. This includes some larger platforms, although often still human-in-the-loop for strike decisions, like the Turkish Bayraktar TB2, which got a lot of attention early on.
Yeah, I remember those.
But the real story, according to the sources, the thing that's fundamentally changing the battlefield calculus is the explosion in the use of smaller, cheaper, and increasingly autonomous systems, particularly loitering munitions and even just repurposed commercial quadcopters.
And the numbers involved, are they quantified?
The sources try to pull together estimates from open sources, and the figures are genuinely eye-watering. Some reports reference suggest somewhere around 10,000 to 20,000 tactical drones operated overall since 2022 by both sides.
10 to 20,000, wow.
And looking at more specific examples cited in the material, there were reports suggesting around 200 Russian Lancet strikes in early 2025 alone. The Lancet is a key Russian loitering munition with autonomous capabilities. That number gives you a sense of the sustained, high-tempo use of just one specific type.
200 strikes in just a few months with one system type.
Exactly. And then on the, let's say, lighter, more numerous end of the spectrum, the sources note 10,000 quadcopter sorties overall. These are often basic commercial drones like DJIs, modified to drop grenades or conduct surveillance, many operating with increasing levels of automation for navigation and targeting assist. It really highlights the democratization of this kind of aerial capability.
Those numbers are hard to wrap your head around. What kind of actual impact have these tens of thousands of drones had on the fighting? It sounds like it must be more than just nuisance harassment.
Oh, far more. The sources indicate these drones, especially the loitering munitions, have inflicted really significant attrition on both high-value equipment tanks, artillery, air defense systems, and personnel. Autonomous loitering munitions, like Russia's Lancet 3 or newer versions, are specifically highlighted for their ability to autonomously home in on targets once they've been identified, often using their onboard AI vision systems to make those final tracking adjustments and ensure the hit, even if the target tries to move or uses countermeasures like smoke.
So they can lock on and follow through autonomously.
Yes. And the sources pull out some specific case studies or observed trends from the conflict that illustrate this impact. One really notable development mentioned is the use of anti-armor swarms.
Swarms against tanks.
Yeah. Coordinated attacks using multiple loitering munitions hitting roughly the same area or target set simultaneously. Systems like those Lancets, or the U.S.-supplied Phoenix Ghost drones, have reportedly destroyed dozens of armored vehicles in localized battles using these swarm or saturation tactics. It's not just picking off one tank here and there, it's using numbers, potentially coordinating the timing of impacts to overwhelm the defenses of an armored unit. This is having a real impact on specific battles and tactical maneuvers.
Overwhelming defenses through sheer numbers.
Exactly. Another striking impact mentioned is air defense evasion. The sources point to numerous instances, particularly Ukrainian suicide drones, striking targets deep inside Russian territory. We're talking hundreds of kilometers, including facilities near Moscow and hitting vessels of the Russian Black Sea Fleet. Often, these strikes reportedly achieve penetration with minimal warning from traditional air defense systems.
How are they getting through?
It demonstrates how these relatively low-cost, often small, autonomous systems, maybe flying very low, using complex terrain-following routes programmed in advance or just coming from unexpected directions, can really challenge traditional, expensive, layered air defenses that were primarily designed to counter faster, higher-flying threats like fighter jets or cruise missiles. They exploit gaps or sometimes just present too many simultaneous targets for the defense system to handle effectively.
So they're finding the seams in established defenses.
And it's not just offense. The sources also mention autonomous systems being used effectively in defensive roles, too. They cite systems like the Russian repellent electronic warfare system, which is claimed to be AI-enabled and automatically engages approaching enemy drones by jamming their control or navigation signals. This shows AWS being used as automated sentries or local area defenses against drone threats.
And the pace of development, it seems like the war itself is driving incredibly rapid innovation. Were there any brand new developments mentioned in the sources, maybe from just recently in 2025?
Yes, the sources absolutely highlight the speed of innovation being forced by the conflict. One specific item noted is Russia's new V2U AI-guided loiterer, which was reportedly revealed publicly in June 2025.
V2U. Any details on what makes it new?
Specifics are often limited or based on initial reports, but the system is rumored to possess more advanced autonomous navigation capabilities. This could allow it to operate more effectively and independently in complex environments, perhaps with better resistance to jamming. It's also rumored to have more sophisticated strike patterns, potentially allowing it to choose how best to approach a target based on the target type or its defenses, rather than just a simple dive. It points to this continuous evolution towards smarter, more capable autonomous functions being packed into even these relatively small, disposable platforms.
It's like a real-time arms race playing out month by month.
Very much so.
All these examples, particularly the scale we're seeing in Ukraine, really seem to underline a concept the sources keep coming back to, the attritable doctrine. That sounds like a really key idea defining how these systems are being used. Can you explain what that means?
The attritable doctrine is absolutely central, yeah. It basically means using systems that are cheap enough and numerous enough that you can afford to lose them. They are explicitly designed to be expendable or attritable. You don't have the same kind of concern about losing one as you would about losing, say, a multi-million-dollar fighter jet or a main battle tank with a crew inside. The cost of a single advanced air defense missile used to shoot down one of these drones might be many, many times the cost of the drone itself.
So the economics are completely different.
Totally. And this doctrine is heavily enabled by the incredibly low cost per engagement of many of these systems.
Right, the cost factor.
Exactly. The sources hammer this point home. Basic commercial quadcopters modified for dropping small bombs can cost just a few thousand US dollars, maybe even less. Purpose-built loitering munitions might be in the range of, say, $20,000 each, maybe more, maybe less, depending on sophistication.
Which sounds like a lot, but compared to traditional military hardware.
It's peanuts. Orders of magnitude lower than the cost of flying a mission with a manned aircraft or the cost of many traditional guided missiles, which can run into the hundreds of thousands or millions of dollars each.
Okay.
And this low cost is precisely what enables those swarming tactics we talked about. You can realistically field hundreds or even thousands of these cheap drones that are designed with the expectation that many will be shot down or fail. They can simply overwhelm more expensive, sophisticated defenses that might be very capable, but simply cannot engage that many targets simultaneously, or doing so would bankrupt the defender.
So you just saturate the defenses.
Saturate them or make it economically unsustainable to keep shooting them down. And critically, the sources note that the production lines and supply chains seem to be keeping pace, at least to some extent, with this high rate of attrition. Thousands of these drones are reportedly being delivered annually to the battlefield, ensuring a constant supply to feed this attritable warfare model.
Okay, so putting it all together, we're seeing different levels of autonomy powered by converging tech being used at an absolutely unprecedented scale on the modern battlefield, largely following this doctrine of cheap, numerous, disposable systems designed to overwhelm defenses. It's fundamentally changing tactics, economics, everything.
It truly is. It's a paradigm shift in many ways. And understanding how these machines actually do what they do, how they see, think, and act, is the next really interesting piece of this puzzle.
Right. This is where it gets really fascinating, I think. How do these machines actually see the world around them, understand what they're seeing, and then make decisions based on that information, all without direct human guidance in that moment? The forces talk about complex perception stacks. What does that mean?
Yeah, perception stack is a good term. An autonomous system doesn't just look at the world like we do. It processes information through multiple layers, starting with raw sensor data and ending up with actionable information like that's a target, engage.
So it's a chain of processing.
Exactly. It needs to take the raw data coming in, maybe it's the pixels from a camera feed, the radio wave reflections from a radar, or the point cloud map from a LiDAR sensor, and turn that into something meaningful, something that allows it to identify objects, track them, understand the environment, and figure out what's a threat or a target versus what's just background clutter or a friendly force.
And how does something like that YOLO-9 object detection fit into this stack?
Okay, so YOLO-9, which we mentioned stands for You Only Look Once, is a specific type of algorithm that's incredibly fast and efficient at scanning an image or a video frame. Unlike older methods that might have analyzed an image patch by patch, YOLO looks at the whole image at once.
Hence the name.
Hence the name, yeah. And by doing that, it can very rapidly identify and classify different objects within that frame, drawing those bounding boxes around them. It learns to recognize specific things, tanks, trucks, certain types of LiDAR installations, maybe even groups of people, often with pretty high accuracy, even if they're moving fast or partially hidden.
So it picks out the important stuff from the visual noise.
Right. And that processed output, the location and classification of potential targets, is then fed directly into the system's next stage, which might be the decision-making logic, or, in the case of a weapon, the missile guidance loop. That loop uses the target's location and movement information to tell the weapon precisely where to go, adjusting its own flight path constantly to ensure an interception or a hit.
So it's not just seeing a picture, it's analyzing it in real time to find specific relevant items and track them.
Precisely. And as we touched on, the sources also mention other approaches like vision transformers, VIT. These are a bit different, maybe more recent. While algorithms like YOLO often focus on localized features, vision transformers can process the image more holistically, looking at the relationships between different parts of the scene. This might allow for a deeper understanding of the context. Is that vehicle parked or moving? Is it near friendly troops? That kind of broader scene understanding.
And these systems aren't usually relying on just one camera, are they?
No, definitely not, especially the more sophisticated ones. They almost always use sensor fusion. This means combining data streams from multiple different types of sensors.
Like layering different views.
Exactly. Maybe they have a standard electro-optical camera for daylight vision, an infrared camera that sees heat signatures, great for night or spotting engines, maybe radar, which works well in fog or smoke, or LiDAR, which uses lasers to build a very precise 3D map of the immediate surroundings. By fusing the data from all these different sensors, the system builds a much more robust, reliable picture of what's going on. If a target is camouflaged effectively against visual detection, maybe its heat signature still pops out on the infrared sensor. If it's foggy, the radar might still see it clearly. Combining these inputs makes the system much harder to fool, more resilient to different weather conditions, and better at seeing through attempts at concealment.
That multi-sensor approach definitely sounds like it makes them more robust. We mentioned the Edge AI chips earlier, putting the processing power right on the drone, but the sources also specifically call out low-powered neuromorphic chips. What's the big deal with those for drones?
Neuromorphic chips are really interesting. They're processors designed using principles inspired by how the human brain is structured and how it functions.
Brain-inspired computing.
Kind of, yeah. Unlike traditional computer chips that process information sequentially or in parallel using standard digital logic, neuromorphic chips use networks of artificial neurons and synapses to perform computations, often in an analog or mixed signal way. The key advantage, especially for something like a small drone operating on battery power, is their incredible energy efficiency.
They use less power.
Way less power for certain types of tasks, particularly things like pattern recognition and processing noisy sensor data, which brains are exceptionally good at. By mimicking this biological efficiency, neuromorphic chips can perform really complex AI tasks like that real-time object detection, tracking multiple targets, making navigation decisions using significantly less battery power compared to conventional processors doing the same job.
And what does that enable?
Well, the sources suggest this technology holds the promise of enabling things like 24-hour drone loitering. Imagine a small, relatively inexpensive drone being able to stay airborne, circling over an area, providing persistent surveillance, or being instantly ready to strike for an entire day or night without needing to land for refueling or battery swap. That kind of persistence completely changes the operational possibilities for these smaller systems.
A full day airborne on battery power. That's a game changer for surveillance and rapid response.
Mhm.
Okay, what about the swarms again? When you have maybe dozens or hundreds of these things flying together, how do they manage that incredibly complex coordination without a human directing every single move?
That requires sophisticated swarm algorithms.
Huh.
These are the programmed rules and logic that govern how the individual drones in the group interact with each other and coordinate their collective behavior to achieve the swarm's overall objective.
And there are different ways to program that behavior.
Yes, the sources mention a couple of main approaches. One is that leaderless flocking idea we touched on, inspired by nature. In this model, each drone follows a few simple local rules. Maybe stay about this far from your nearest neighbors, match their average speed and direction, avoid collisions, and steer generally towards the target area. Complex, coordinated group movement, like swirling around a target or searching an area efficiently, can emerge naturally from these simple individual rules without any single drone being designated as the leader.
So the intelligence is distributed across the swarm.
Exactly, it's decentralized, which can make it more resilient if some units are lost. But you can also have hierarchical command structures, as mentioned before. In this case, maybe one drone acts as the flight lead, or a nearby ground station acts as the controller. This leader receives the overall mission instructions and then assigns specific tasks or search sectors to the other drones in the swarm, managing the group's activities more directly. Both approaches have pros and cons depending on the mission.
And whichever approach they use, keeping all those units talking to each other reliably is paramount, especially if the enemy is actively trying to jam their signals.
Absolutely. That robust communication infrastructure is the glue that holds the swarm together. It relies on those technologies like mesh networking, where units relay messages for each other, creating that resilient web. And anti-jam optical links using lasers, which are much harder to detect and disrupt than normal radio signals, providing a secure, high-bandwidth channel for coordination, especially vital under heavy electronic attack. Keeping the swarm connected and coordinated is absolutely fundamental to making it work effectively.
Okay, so this tech sounds incredibly powerful when it works as intended. But what happens when it doesn't? These are machines making potentially lethal decisions based on sensors and algorithms. How do developers try to make these systems robust? How do they handle potential errors or even malicious interference?
That's a critical area the sources discuss. Dealing with failure modes and actively hardening these systems against them. Because autonomous systems, especially ones relying heavily on sensors and AI interpretation, face real threats beyond just getting shot down. Adversaries will actively try to trick them.
Like spoofing.
Exactly. Spoofing is a major concern. This involves feeding the system's sensors false signals to mislead it. For example, sending fake GPS data to make the drone think it's somewhere it isn't, causing it to navigate incorrectly or miss its target area, or using electronic decoys that mimic the signature of a real target to lure the weapon away.
And what about fooling the AI's vision?
That's another threat. Adversarial camouflage or adversarial examples. These are patterns or techniques specifically designed to confuse the AI's computer vision system. It might be a physical pattern painted on a vehicle that makes the AI algorithm misclassify it as something harmless or fail to see it altogether. Or it could be subtle manipulations of sensor input that cause the AI to make incorrect judgments.
So how do you defend against being tricked like that?
Developers build in multiple layers of hardening measures. One key strategy is using those multiple diverse sensor types we talked about and implementing rigorous multi-sensor cross-checks. The system constantly compares the data coming from its camera, its radar, its infrared sensor, etc. If the camera sees a tank, but the radar sees nothing there, or the infrared signature doesn't match, the system can flag that as suspicious or potentially unreliable input.
Cross-referencing the data.
Right. They also use anomaly detection algorithms. These algorithms are trained to recognize normal patterns of sensor readings and system behavior. If something suddenly looks weird or statistically unlikely, a GPS signal jumping erratically, a sensor reading going haywire, the system can identify it as a potential anomaly, possibly indicating spoofing, jamming, or a component failure.
Looking for things that don't fit.
Exactly. Building in redundancy is also crucial. Having dual sensors for critical functions, multiple communication links using different frequencies or methods like radio and optical, backup navigation systems like SLAM plus inertial. This ensures that if one component fails or is compromised, the system can hopefully continue its mission using the backup.
Having spares built in.
Essentially. And finally, implementing sophisticated fail-safe behaviors is absolutely essential. This means programming the system with clear instructions on what to do if it encounters a critical error it can't resolve, if it loses communication with its controllers for too long, if it detects it's way off course, or if its confidence in target identification drops below a certain threshold.
What kind of fail-safes?
It could be programmed to automatically abort the attack, circle back to a designated safe area, return to its launch point if possible, or in some cases even self-destruct in a way that minimizes collateral damage, rather than risking hitting the wrong target or falling into enemy hands intact. It's a constant, ongoing effort to anticipate potential failures and design robust defenses and safe fallback modes.
So it's not just about making the system smart, it's about making them resilient and predictable, even when things go wrong or someone tries to trick them.
Absolutely. The technical challenges are immense, and the countermeasures game is evolving just as quickly as the autonomous capabilities themselves. It's a continuous cycle.
Okay, so if the technology is moving this fast, and it's clearly being used on battlefields right now, and it presents all these complex technical challenges, what about the rules? What does international law and policy actually say about these systems? We're talking as of June 2025 here. Is there a legal framework that's managing to keep up with the pace of this technology?
That is a major area of intense international focus, debate, and development. And it's one where the sources highlight some really significant recent movement, actually. A key venue for these discussions has been the UN Convention on Certain Conventional Weapons, CCW in Geneva.
The CCW, right? They've been talking about this for a while.
They have. The CCW has had a specific group of governmental experts, GGE, meeting on lethal autonomous weapon systems, or laws, since way back in 2013. For years, they were mostly focused on understanding the issues, defining terms, debating whether existing international law was sufficient, or if completely new rules were needed.
Lots of discussion, but maybe not much concrete action.
For a long time, yes. But the sources point to a really significant development in this ongoing process. There is now formal agreement, backed by over 120 states, to actually launch dedicated treaty talks specifically on AWS. And according to the sources, these formal negotiations reportedly kicked off in May 2025.
Wow. Okay, so they've moved from just discussing it to actually starting negotiations on a potential treaty. That sounds like a big step.
It's a very big step. It signals a growing international consensus, or at least a recognition by a large majority of states, that the existing legal frameworks might not be adequate on their own, and that new legally binding rules are probably necessary to effectively govern the development and use of these powerful systems.
But even without a new treaty yet, existing international humanitarian law, IHL, the laws of war that does still apply to all weapons, including autonomous ones, right? Things like distinction and proportionality.
Yes, absolutely. That's a crucial point. The fundamental principles of IHL, which govern how warfare must be conducted, apply universally to all means and methods of warfare. That definitely includes autonomous weapons.
So what are those key principles again?
The big ones here are the principle of distinction, which requires parties to a conflict always distinguish between combatants and military objectives on the one hand, and civilians and civilian objects on the other, and only direct attacks against the former. And the principle of proportionality, which prohibits attacks where the expected harm to civilians or civilian property would be excessive or disproportionate compared to the concrete and direct military advantage anticipated from the attack.
Okay, so AWS have to be able to distinguish civilians, and they have to ensure their attacks aren't excessively harmful to civilians relative to the military gain.
That's the legal requirement. However, critics, and this is heavily highlighted in the sources, raise very serious questions about whether current AI systems can reliably make these incredibly complex, context-dependent judgments in the chaotic, ambiguous, and often unpredictable reality of a battlefield.
Can an algorithm really tell the difference between a surrendering soldier and an active combatant in all situations? Or weigh the military value against potential civilian deaths with human-like judgment?
That's precisely the concern. Can an AI truly distinguish combatants from civilians reliably under pressure with imperfect sensor data in complex urban environments? Can it genuinely assess the proportionality of an attack, considering potential reverberating effects on the civilian population with the necessary nuanced human judgment? This perceived gap, the potential inability of current AI to reliably apply these fundamental IHL principles and all the messy complexity of real war, is a major driving force behind the calls for new regulations, and specifically for retaining meaningful human control over the use of lethal force.
So while the old rules technically apply on paper, there's a huge debate about whether the technology is actually capable of complying with them in practice, and whether relying on these systems inherently risks violating IHL.
That's a fair summary of the core legal tension, yes.
Okay, beyond these international treaty talks, what are individual countries doing? Do different nations have clear policies on how they're developing or planning to use AWS? Are they all on the same page?
Not at all. The sources contrast several different national approaches, highlighting the real lack of a uniform global standard right now. For instance, the U.S. Department of Defense has Directive 3000.09. This policy requires appropriate human judgment in the use of lethal force.
Appropriate human judgment. What does that mean in practice?
Well, while the directive doesn't impose an outright ban on fully autonomous weapons, it generally mandates that humans must maintain sufficient control over the system to exercise that appropriate judgment. In practice, this often translates to requiring at least human-on-the-loop, HOTL control, for most offensive systems, meaning a human supervisor who can intervene and override. However, as we noted, the policy does allow for exceptions, particularly for certain high-speed defensive tasks like missile defense, OTL, where human reaction time is deemed insufficient.
So supervised autonomy is generally required, but with exceptions. How does that compare to, say, China?
The U.S. approach is often contrasted with China's stance. China is heavily focused on integrating AI across its military, a concept often referred to as intelligentized warfare. While China has publicly stated it supports international efforts to regulate AWS and prevent their misuse, its specific internal rules and operational guidelines regarding the levels of autonomy permitted are reportedly much less transparent than those of the U.S. The sources also suggest that China's approach to export controls on related AI and drone technologies might be less stringent, which contributes to those proliferation concerns we'll likely talk about later.
Less transparency and potentially looser export controls. What about Russia?
Russia's public stance also lacks a formal ban on developing or using AWS. They are actively exploring advanced modular drone fleets and seem open to using highly autonomous systems for air and sea defenses. Officially, the sources indicate they insist on retaining human oversight for offensive strike decisions. However, the observed battlefield use in Ukraine, particularly with loitering munitions that appear capable of autonomous final target engagement, suggests that their practical application might be pushing the boundaries of that stated policy or interpreting oversight quite broadly.
So it really sounds like a patchwork of national policies. Nobody's implementing a complete ban, transparency varies wildly, and maybe practice doesn't always line perfectly with stated policy.
That's a good way to put it. There's a real lack of global coherence right now.
And what about broader AI regulations? We hear a lot about governments trying to regulate AI for civilian uses, like in self-driving cars or facial recognition. Does any of that apply to military AI? The sources mentioned the EU AI Act.
Yes, and this is a really key point the sources highlight, because it contributes to a significant regulatory gap. The EU AI Act, which was finally passed in 2024 after much debate, is a landmark piece of legislation. It aims to regulate civilian AI systems based on their potential risk level across the European Union.
Yes.
But the sources explicitly state that the final text of the EU AI Act explicitly exempts military AI from its scope and regulations.
Completely exempt.
Yes. AI systems developed or used exclusively for military purposes or national security are carved out. This means all those comprehensive rules and requirements the EU developed for things like risk assessment, bias detection, data governance, transparency, human oversight, and safety for civilian AI systems. They simply do not apply to AI being used to develop weapons, guide missiles, identify targets, or support military decision-making.
Wow. So that leaves a huge area unregulated by arguably the most comprehensive AI law passed so far.
Exactly. It creates a substantial regulatory vacuum specifically for military AI, not just in the EU, but potentially influencing approaches elsewhere. It effectively sets up a parallel system. One set of increasingly stringent rules for civilian AI, and another much less defined, much less regulated, and far less transparent space for military applications.
That regulatory gap, especially combined with the speed of the tech, seems really concerning. What about when things go wrong? If an autonomous system makes a mistake and causes civilian deaths or destroys the wrong target, who is legally held accountable under current frameworks?
That brings us to one of the absolute thorniest and most intensely debated legal challenges: accountability and attribution. Under traditional international humanitarian law, commanders are ultimately responsible for the actions of the forces under their command, including the lawful use of weapons. The principle is that humans must remain accountable for any violations of the law of armed conflict.
Okay, commanders are responsible. Seems clear enough.
It sounds clear, but it gets incredibly murky with highly autonomous systems. The sources point to a significant ongoing debate and what many legal experts are calling a potential responsibility gap. When an autonomous system, operating perhaps in HUTL mode without direct human intervention in that final kill decision loop, makes a critical error, maybe due to flawed sensor data, an unexpected environmental factor, or an edge case in its algorithm, and that error results in unlawful civilian harm, who precisely is legally responsible?
Yeah, who do you charge?
Exactly. There are profound legal questions and intense debates about how you would actually hold an individual legally liable. Is it the operator who simply activated the system hours earlier? Is it the commander who authorized its deployment in a general area based on the intelligence available at the time? Is it the programmer or the team of developers who wrote the millions of lines of code months or years before trying to anticipate battlefield conditions? Could any of them meet the legal standards for criminal intent or negligence when the machine acted based on its programming in unforeseen circumstances?
It seems incredibly difficult to assign that direct legal responsibility.
It is. This difficulty in clearly tracing and assigning legal and indeed moral responsibility for the outcomes generated by an autonomous system is a key driver behind those international calls for stronger requirements for meaningful human control, ensuring that there's always a human sufficiently involved in the decision-making process to be genuinely accountable for every single lethal strike, closing that potential responsibility gap.
It really is a thorny problem. The machine makes the decision in the moment, based on its code and sensors, but a human initiated the process somewhere way up the chain, maybe miles away or months earlier writing the software. Pinpointing legal and moral responsibility.
That's tough.
Extremely tough. The chain of causality and decision-making becomes far more complex and diffuse than with traditional weapons operated directly by humans. Okay, so beyond these really complex legal questions and the challenge of accountability, there are also profound ethical debates swirling around autonomous weapon systems. These aren't just technical or legal puzzles. They really touch on fundamental moral questions about warfare, killing, and what it means to be human. What are the main moral lines being drawn in this debate, according to the sources?
The sources clearly highlight a distinct moral split, two fundamentally opposing viewpoints, in the ethical debate surrounding AWS.
Okay, what's the argument for them, ethically speaking?
Well, on one side, proponents argue that autonomous systems could, counterintuitively perhaps, actually reduce overall human casualties in conflict, both for one's own military personnel by keeping soldiers out of direct harm's way in the most dangerous situations, sending machines instead, and potentially even for civilians on the other side.
How could they potentially reduce civilian casualties?
The argument is that machines aren't subject to human emotional factors like fear, anger, fatigue, stress, or a desire for revenge. These human factors can tragically lead to mistakes, panicked decisions, and unintended civilian harm in the fog and friction of combat. Autonomous systems, the argument goes, if programmed correctly with strict rules of engagement and equipped with reliable sensors, could theoretically be more precise, more discriminate, and more consistent in applying force according to the laws of war than humans operating under extreme duress.
So the argument is machines might be more ethical decision makers in some ways because they lack disruptive human emotions.
That's essentially the core of the argument for their potential ethical benefit: increased precision and potentially reduced collateral damage by removing volatile human factors from the immediate kill decision.
Okay, and what's the counter argument, the critique?
On the other hand, critics raise extremely serious moral and humanitarian costs they believe are inherent in delegating lethal decision-making to machines. They warn forcefully about the significant risk of the dehumanization of warfare.
Dehumanization. What does that mean in this context?
The core concern here is the loss of moral agency. Moral agency is that uniquely human capacity to make ethical judgments, to understand the gravity of taking a human life, and to be held morally accountable for those decisions. When the decision to end a human life is delegated to an algorithm, critics argue, something fundamental is lost. Outsourcing this ultimate, incredibly weighty decision may, over time, erode our collective respect for the sanctity of human life itself. It risks leading to a future where humans are viewed less as individuals with inherent dignity and worth, and more as just data points, obstacles, or targets to be processed efficiently by an algorithm.
Treating people like objects in the machine's code.
Exactly. This risk of losing empathy, of normalizing killing by making it a cold, calculated, automated process removed from human conscience, is sometimes described in the sources as leading towards an ultimate dehumanization of conflict.
So the debate isn't just about whether the machine can make the decision effectively or precisely based on its programming, but whether it should morally be allowed to make that kind of uniquely human decision at all.
That's the heart of the ethical objection, yes. The should question.
What does the wider public think about this? Is this just a debate happening among ethicists, lawyers, and military planners, or does it resonate more broadly?
The sources actually inject some relevant public opinion data here, suggesting this is a deeply felt concern for many people around the globe. A global Ipsos poll from 2021, mentioned in the material, found a pretty significant majority of people surveyed across numerous countries specifically. The poll found approximately 61% expressed clear opposition to the development and use of fully autonomous lethal weapons.
61% against. That's substantial. Did the poll indicate why people felt that way?
Yes. According to the sources discussing the poll, the primary reason cited by respondents for this widespread opposition wasn't necessarily about fears of technical malfunction or accidents. It was a clear, fundamental, moral conviction that, simply put, machines should not be allowed to kill. It was an objection rooted in ethics and morality, not just practicality.
That poll data really reinforces the idea that there's a widespread, almost intuitive resistance in many cultures to handing over the power of life and death to a machine. It touches on something fundamental about human responsibility.
It certainly seems to. And it ties right back into that incredibly difficult question of accountability we were just discussing. The sources implicitly pose a really thought-provoking rhetorical question, one that kind of encapsulates these intertwined moral and legal concerns. If an algorithm makes an error, maybe it misinterprets sensor data or encounters a situation its programmers never anticipated, and someone, a civilian, is killed unintentionally as a result, and the system was operating fully autonomously, who really stands trial? Who bears the moral weight, the guilt, the responsibility for that death? Is it the programmer who wrote the code, possibly years earlier, trying their best? Is it the commander who deployed the system into that complex environment? Or is it the machine itself, which, of course, has no conscience, no feelings, no capacity for moral reasoning or remorse?
These are profound, deeply unsettling questions. Questions that we as a global society are really only just beginning to seriously grapple with as this technology rapidly moves from science fiction concepts into battlefield reality.
They absolutely are. And it's important to remember these ethical and legal debates aren't happening in some isolated philosophical bubble. They're playing out against a backdrop of intense geopolitical competition and accelerating arms race dynamics.
Right. This technology isn't developing in a vacuum. The development and deployment of autonomous weapon systems are fundamentally reshaping the global power balance and driving massive investments and strategic shifts. What are the major geopolitical and economic forces at play here, according to the source material?
The sources point to initiatives like the U.S. Replicator program as a prime example of how major military powers are reacting to this new technological landscape and the perceived actions of rivals.
Replicator, launched in 2023, right? What's the goal there?
The stated goal is to rapidly field thousands of autonomous systems, primarily drones, across multiple domains, doing it quickly and at scale. The source material specifically mentions a 2025 claim or goal from the U.S. Department of Defense of having thousands-strong drone fleets field-ready within months as being central to this program's intent.
Thousands of drones ready in months. That's incredibly ambitious. Why the rush?
It's explicitly framed in the sources as a strategic imperative, largely a direct response to growing concerns about the capabilities and intentions of potential adversaries. Specifically, the sources mention concerns about China's rapid littoral buildup, meaning its significant and increasing military presence, naval power, and missile capabilities in coastal areas, particularly focused around Taiwan and the South China Sea. China is also known to be making huge strides in AI and integrating autonomous systems into its own military. So Replicator is seen as a way for the U.S. to counter that perceived challenge, using large numbers of relatively cheaper, attritable autonomous systems to offset potential quantitative disadvantages or counter specific threats, like a potential invasion force. It's a clear signal of a major power accelerating its development and deployment of these systems to maintain a strategic edge. It absolutely has arms race characteristics.
So it's partly a direct competitive reaction to specific concerns about rivals like China and their growing capabilities.
Mm-hmm.
But the sources also point out a really troubling aspect of this technology. It doesn't seem like it's going to stay confined to just the major military powers for long.
That's a critical concern discussed extensively in the material proliferation pathways. Unlike, say, nuclear weapons technology, which requires massive industrial infrastructure and rare materials, the sources highlight that much of the underlying technology needed to develop or acquire significant autonomous capabilities is becoming increasingly accessible, affordable, and democratized.
How so?
Well, think about commercial quadcopters. Drones made by companies like DJI, originally designed for photography or hobbyists, are available globally for relatively low prices. And they can be, and are being, easily modified for military surveillance or even to drop small munitions. We see that constantly in Ukraine. Furthermore, critical software components like open-source autopilots, the flight control software that can make a drone fly itself along programmed routes, are publicly available. And even open-source AI kits for things like object detection and tracking are becoming easier to find, adapt, and integrate.
So the building blocks are getting cheaper and easier to get hold of.
Exactly. This dramatically lowers the barrier to entry. It means that not just major powers, but smaller nations, non-state actors like militant groups or insurgents, and potentially even terrorist organizations or sophisticated criminal networks could acquire or build their own autonomous drone capabilities much more easily than they could acquire traditional advanced weaponry. This raises the serious risk of uncontrolled spread proliferation and the potential use of these systems by groups operating outside international norms and laws. It makes the technology far harder to track and control than technologies with more significant choke points.
It sounds like the genie might already be out of the bottle in terms of basic capability diffusion. And related to that speed of development and potential for widespread use, the sources warned about a significant escalation risk that seems inherent in these autonomous systems.
They do, and it's a really chilling prospect. Autonomous systems can operate at machine speed. They can perceive, decide, and act in milliseconds or microseconds far faster than any human could possibly react or intervene. The sources point out that these incredibly fast microsecond decision loops could lead to extremely rapid, unintended escalation in a crisis situation.
How might that happen?
Imagine a tense border standoff. An autonomous defense system on one side, maybe operating in HUTL mode, gets a false positive reading. Perhaps a flock of birds is misidentified by its algorithm as incoming drones, or sensor interference creates a ghost target. The system, following its programming, might launch a defensive strike before any human operators even see the anomaly on their screen, let alone have time to analyze it, communicate with the other side, or engage in any kind of de-escalation.
And that defensive strike could be misinterpreted by the other side.
Exactly. The other side's autonomous systems, or even human operators reacting instantly to what looks like an unprovoked attack, might retaliate immediately. You could have a cascade of actions and reactions happening at machine speed, potentially spiraling into a significant conflict before diplomats can even get on the phone or military commanders fully understand what triggered the initial event. This risk of rapid, unintended conflict simply outrunning human decision-making timelines and diplomacy is a major geopolitical concern. Some analysts refer to it as the terrifying potential for flash wars. The speed of the machine could literally bypass human control in a crisis.
The potential for an algorithm's mistake, or just an unforeseen interaction between two autonomous systems to trigger a conflict before anyone can hit the brakes, that is a really sobering thought.
It absolutely is. And the sources also briefly touch on how this technology is influencing specific regional dynamics beyond the major power competition. They cite examples like Iran exporting its relatively inexpensive Shahed drones to various non-state groups across the Middle East, which has significantly altered battlefield tactics and defensive challenges in places like Yemen or against shipping. Or how China's accelerating advancements in the Indo-Pacific are pushing other nations in the region, Japan, South Korea, Australia, Taiwan, to rapidly invest in their own similar autonomous technologies as a countermeasure, further fueling regional arms races and increasing the density of these systems in potential flashpoint zones.
So it's a truly global phenomena, driven by superpower competition, enabled by increasingly accessible technology, spreading to regional conflicts and non-state actors, and carrying this inherent risk of rapid unintended escalation.
It's a very complex, dynamic, and frankly concerning picture that's influencing military doctrines, defense budgets, and international security relationships right across the board.
Okay, so if these autonomous weapon systems are becoming so prevalent, so capable, and potentially so destabilizing, what's being done on the other side of the equation? What about defending against them? It sounds like this rapid advancement on the offense side must be creating a whole new arena for that classic military cat-and-mouse game of offense versus defense.
It absolutely is. As autonomous offensive capabilities, especially swarms, become more potent, there's a parallel, intense effort underway to develop effective anti-AWS tools and countermeasures. The sources describe a whole range of emerging defenses being developed and, in some cases, already deployed.
What kind of defenses are we talking about?
Well, some are extensions of traditional methods. Things like more sophisticated electronic jammers designed specifically to disrupt the communication links, whether radio frequency or maybe even those optical links that autonomous systems, especially swarms, rely on to function and coordinate, or jammers targeting their GPS or other satellite navigation signals to make them get lost.
Trying to cut their lines of communication or mess with their navigation. Makes sense. What else?
Then you have more advanced kinetic and directed energy options. The sources mention high-energy lasers quite a bit. These are being developed and tested specifically to physically shoot down drones, especially large numbers of them in a swarm, by focusing a powerful beam of light to burn through their airframe or fry their sensitive electronics. There are also dedicated physical measures like launching anti-drone nets from other drones or ground systems to entangle them, or specialized anti-drone guns that might fire nets or use focused electronic pulses to disable targets at short range.
Lasers and nets. Sounded sci-fi, but apparently becoming reality.
Very much so. And importantly, the effort to counter autonomous systems is also becoming increasingly AI-enabled itself. It's not just humans trying to figure out how to stop the machines. We're seeing the development of AI-driven jammers, or what's sometimes called cognitive electronic warfare, EW systems.
Cognitive EW, what's that?
These systems use machine learning algorithms to rapidly detect, analyze, and identify the specific signals being used by enemy drones in real time. Then they can automatically adapt their own jamming signals or electronic countermeasures to be most effective against that specific threat, essentially trying to learn and counter the opponent's technology on the fly much faster than a human operator could manually adjust settings.
So using AI to fight AI.
Exactly. And perhaps the most telling indicator of where this is heading is the development of drone-on-drone interceptors. These are autonomous drones specifically designed and programmed to hunt down and destroy other drones, including potentially engaging and breaking up incoming enemy swarms, kinetically, basically, dogfighting drones.
So it's not just humans trying to counter machines anymore. It's increasingly machine versus machine in the skies above the battlefield.
That seems to be the trajectory, yes. However, the sources consistently highlight a significant and persistent challenge for the defense side in this equation: the cost asymmetry.
Right, we talked about the low cost of the attacking drones.
Exactly. That attritable doctrine means the attacking swarms are often composed of many relatively cheap, disposable systems, costing maybe thousands or tens of thousands of dollars each. Defending against that swarm using much more expensive interceptor missiles, which might cost hundreds of thousands each, or complex electronic warfare systems, or even those high-energy lasers, which have huge development and deployment costs, can be significantly more costly per engagement than the cost of the attacking drone being neutralized.
So it might cost you way more to shoot down the drone than it cost the attacker to send it.
In many current scenarios, yes. That economic reality currently tends to favor the offense in this specific aspect of warfare. It makes it financially challenging, maybe even unsustainable, for defenders to reliably stop large, persistent swarms indefinitely if the attacker is willing to keep sending cheap drones. You might win the engagement, but lose the economic battle.
So it's often cheaper to launch the swarm than to stop it reliably. That's a really tough equation for defenders.
It's a major strategic challenge they're grappling with. And the sources conclude this section with a really important insight. Autonomy isn't just being bolted onto existing weapons as a new feature anymore. It's rapidly evolving into something much more fundamental. It's becoming a core strategic layer, deeply integrated into overall military planning, network architectures, command and control systems, intelligence gathering, logistics, and defense strategies. It's changing the basic assumptions about how militaries will need to organize, train, and fight in the future.
That really brings us full circle from that initial picture we painted of a single menacing swarm in the sky. It's not just about individual weapons, it's a fundamental shift in military capability and thinking that impacts almost everything.
It really is. It's permeating throughout the modern military landscape. And that leads us naturally towards our closing synthesis, trying to pull all these complex threads together.
We've covered a tremendous amount of ground today. We've gone from the basic definitions, what even is an autonomous weapon, the different loops of human control, through the enabling technologies like AI, vision, and edge computing, then plunged into the sobering reality of their widespread use in recent conflicts, especially Ukraine, and the attritable doctrine driving that. We have explored the complex legal and ethical debates they ignite, the accountability gap, the geopolitical arms race dynamics, the proliferation risks, the escalation dangers, and finally, the cat-and-mouse game of countermeasures. The source material across all these different facets presents a really clear central tension, a core dilemma that runs through this entire topic, and one that feels critical for all of us as citizens, as people living in this world to understand as this technology continues its rapid advance.
And that core tension, weaving through all the sources, is essentially the difficult balance between, on the one hand, the undeniable potential benefits offered by this rapid innovation in autonomous systems, benefits like potentially reducing risk to your own soldiers or achieving unprecedented speed and precision in certain military tasks, and, on the other hand, the very serious, very urgent need for maintaining meaningful human control, implementing robust safety measures, and establishing careful international regulation, all to prevent catastrophic unintended consequences, to curb dangerous proliferation, and fundamentally to avoid the further dehumanization of armed conflict.
It boils down to that fundamental challenge. How do we harness the undeniable power and speed of these machines, perhaps even use them for defensive good in some cases, while absolutely ensuring that humanity retains ultimate control over that most profound and irreversible decision, the decision to take a human life?
Precisely. That's the tightrope we're walking. And the sources effectively leave us, and you, the listener, with a really important forward-looking perspective. It's presented less as a prediction and more as both a challenge and a profound responsibility for the future we're collectively creating right now. The code that guides a drone today, the algorithms making those complex calculations, and in some cases, lethal decisions. That same logic, that same capability could very well guide the course of conflict itself on a much larger scale in the future.
So the question becomes, are we, as a global society, developing the wisdom, the foresight, and the collective will necessary to understand the full implications of this incredibly powerful technology? Are we ready and wise enough to write that future responsibly? It's a question that moves far beyond just the technical specifications or the latest battlefield reports. It becomes a fundamental question about our values and our stewardship of technology as this era of autonomous warfare truly dawns.
Indeed. A critical question for our time.
Thank you for joining us for this deep dive into the complex and rapidly evolving world of autonomous weapon systems.